Hello friends, welcome to new lessons. Again we meet here with a new topic of thermodynamics. This is also one of the most important topic in the study of thermodynamics, that is the ideal gas equations. Now I'm quite aware from the class 11 and 12 standards what is ideal gas, the gas which obeys the laws, that is the Boyle's law, Charles law, all those laws. Those are known as the ideal gases. And we'll study about the equations of the states. Now, ideal gas equation of state is an alternative to the tables in equation of state, and the equation of state related pressure, temperature and specific volume will get. These are related to the specific substance and range from the simple to complex also. And simplest is the ideal gas equation. So this is very important because as it is very simple. So the ideal gas equation of the state is PV equals to RT, where R is the gas constant, P is the absolute pressure, T is the absolute temperature, and V is the specific volume. Now R is different for each gas. This is a gas constant, so this will depend upon the different gases. Now that R is equals to RU, that is a universal gas constant by the mass of the gas, and hence you can see this R depends upon the mass of the gas, so it is different for each of the gases. But remember, RU is a universal gas constant and it is constant for all the gases, and m is the molecular mass of the corresponding gas which you want to calculate. So in this pattern, if we'll calculate, then Ru has a fixed value, that is 8.314 kilojoule kilomole Kelvin. And this is the one of the famous equation, that is ideal gas equation of the state. PV by T, P1 V1 by T1 equals to P2 V2 by T2. When there lies a equilibrium between these two states, we use this formula. When the pressure, volume and temperature, all the three parameters are given. Now from the steam table videos, you might be aware with this graph. This is the temperature volume graph, temperature specific volume graph, which is the superheated state, which is the compressed state, which is the saturation part. Now what is the characteristics? It shows about the lowest densities, high temperatures, low pressures. In general, above the critical point there lies the ideal gases equations or the ideal gases state. That you can see this colored picture, pink colored, this is the region for the ideal gases. But all of the gases are not ideal, but they are meant to be ideal for some conditions. Now in study of these ideal gases, there is one more factor, that is the compressibility factor. This is the measure of the deviation from the ideal gas behavior. That means if a gas is deviating from the ideal gas, then how much is it deviating? That is given by this compressibility factor, and it is given as alphabet Z. So equation of this state becomes PV equals to ZRT. For ideal gases, this Z is equals to 1, and for other gases we can have other values less than 1. To plot the information for different gases, we need to define a normalized pressure and temperature. The PR is the pressure, is given as the net pressure by the P at compressibility factor. Sorry, this P is the reduced pressure and T is the reduced temperature, and PCR is the critical pressure and TCR is the critical temperature. So the reciprocal, or you can say the ratio, the ratio of the reduced total pressure to the critical pressure, or total temperature to the critical temperature, gives the reduced pressure and the reduced temperature. And this is very important for the calculation of this compressibility factors. This is a diagram, you can see from the diagram. This is the compressibility factor, and this ideal gas lies after the superheated region is reached. Now talking about the gases in general, at low pressures this PR is less than 1, that is the gases behave as ideal gases regardless of any of the temperatures. Now at high temperatures this TR is greater than 2, that is ideal gas behavior can be assumed, and the deviation of the gas from this ideal gas behavior is the greatest near the critical point. So you need to remember the maximum deviation lies always near the critical point, and as it moves away from it, the deviation decreases, or you can say the compressibility decreases. Now talking about the equation of state, the relationship among the state variables temperature and pressure and specific volume is called the equation of state, and it is given as f of, that is the function of pressure, temperature and volume as the three parameters. Now this, after these many slides, we have come to the topic, that is the ideal gas. This is just for the sake of understanding. I have already told you these are the gases which follows the laws of gases, like the Boyle's law, Charles' law, Pascal's law. Based on our experience in chemistry and physics, we recall the combination of Boyle's and Charles' law. The combination formula for the Boyle's and Charles' law gives us P is equals to NT by V, where R is the constant of proportionality and is called the gas constant, and it takes on different value for each gas. If the gas obeys this relation, it is called an ideal gas. So we often write as PV equals to RT, and for n particles we write PV equals to nRT. Now this is the gas constant, which is equals to universal gas constant divided by the molecular mass of the particular gas. So we'll get the mass m is related to the moles, n is to the substance through the molecular weight of molar mass m. The molar mass is the ratio of the mass to the moles and have the same value regardless of the system of the units. Now you can get the value PV equals to RT. P specific volume can be written as total volume by mass. PV by m equals to RT, and it comes out to be PV equals to mRT. M is related to the moles. Now further more expanding these terms, we will get m by m into mRT, and this m by m comes out to be n. This is the number of moles. R is equals to the Ru is a universal gas constant. So corresponding to these values, we will get this equation, that is P V dash, that is the molar specific volume, is equals to universal gas constant R into T. PV equals to RT. P is the absolute pressure in megapascal or kilopascal. V is the molar specific volume in meter cube per kilomole. R is the universal gas constant 8.314, and T is the absolute temperature. Now some values of universal gas constants are given over here. This is just the conversions, but the most important one is the first two, that is 8.314 kilojoule per Kelvin per kg per mole, and the second one is the 8.314 kilopascal per meter cube per kilomole per Kelvin. Now the ideal gas equation of the state can be derived from the basic principles if one assumes that these are the two conditions which have to be assumed, that is the intermolecular forces are very small and the volume occupied by the particles is small. So if we consider these two terms or these two statements, then it will be very closer to this ideal gas state, and we can use the formulas. So we need to determine the particular gas constant for hydrogen and air. Gas constant is given as R equals to Ru by m. So Ru is 8.314 by m. Now for air and hydrogen we need to calculate. So mass for air is 28.97, that is a mixture of all the gases, and for hydrogen is given as 2. So we will get the different particular gas constant values like this. Next, the ideal gas equation of the state is used when the pressure is small compared to the critical pressure, and when the temperature is twice the critical temperature and the pressure is less than 10 times the critical pressure. These are some points you should remember before using the ideal gas of the state. These are very important. The first two terms, that is the pressure is to be small compared to the critical pressure and the temperature is to be twice the critical temperature. Now we have studied so much about the compressive factor, but we haven't learned about the numerical expression. So here comes the expression, that is PV specific volume equals to ZRT. This is the formula if we use complexity factor Z. So these are the values. For the Z factor is approximately same for all the gases at the same reduced temperature and reduced pressure, and the reduced temperature and pressure volume you can get the ratio of the given pressure by the critical temperature, ratio of the given temperature by the critical temperature, the ratio of the given pressure by the critical pressure. And this is known as the principle of corresponding states. This is one more diagram of compressibility factor. You can see near this critical point there is lot of deviation, but as it moves away the deviation decreases. Now directly coming to this example, calculate the specific volume of nitrogen at 300 Kelvin and 8 megapascal and compare the result with the value of the nitrogen value table. V equals to given as like this. So now the critical temperature and pressure we will get from the table. So 126.2 Kelvin and 3.39 megapascal, and R for nitrogen, that is the gas constant for nitrogen, is given as 0.29, or you can consider 0.3 also. So the reduced temperature and reduced pressure we can easily calculate. Now before going to the ideal gas state, we need two conditions, that is the pressure, the relation between the temperature and the critical temperature, relation between the pressure and the critical pressure. So in this case we find this temperature, the given temperature is greater than twice of the critical temperature. You can see 126 is quite obvious, it is greater than twice the 2.38, and similarly the given pressure is very less than the 10 times of critical pressure. So we use the ideal gas equation state, that is given as PV equals to RT, V equals to RT by P, and we get the specific volume as just substituting the formulas. So clearly shows that nitrogen is in the ideal state. If the system pressure is low enough and the temperature is high, that is P and T are compared to the critical values, gases will behave as ideal gases. Consider to the TV diagram of water, the figure shows the percentage of errors for the volume, and we can find the volume error also. Now this is a useful ideal gas relationship, that is a combined gas law. If we combine all the gas laws, we will get in this way. By writing the ideal gas equation twice for fixed mass and simplifying the properties of the ideal gas of two different states, and we'll get M1 equals to M2, or P1 V1 by RT1 equals to P2 V2 by RT2. But the gas constant is, so you can always say P1 V1 by this, fill in the blanks, I have kept it for you. So P1 V1 by T1 equals to P2 V2 by R2. The gas constant you can calculate also. Similar next example, an ideal gas showing an initial temperature of 25 degrees centigrade undergoes the two processes described below. The process 1 to 2 is the volume is held constant while the pressure doubles, and process 2 to 3 is the pressure is held constant while the volume reduced to 1/3 of the original volume. So what happens in this case? As the process is said from 1 to 3, M1 equals to M3, so we can use the ideal gas equation P1 V1 by T1 equals to P3 V3 by T3. Now given as the volume V3 is V1 by 3 and pressure is double, so again substituting the values, we will get the corresponding temperature T3 value, and in terms of T1, and we'll get T3 value similar to, by putting all the values of T1, we'll get it as T3 equals to minus 74.3. So in this way we can solve simple problems, but we need to analyze the diagram. This is the most important thing. Before progressing to the solution, you must make a diagram corresponding to the question, analyze it, then put the equations. It is just not mugging up the equations and putting them. You need to analyze the situation, what it wants. There are some other laws also. So this was all about the ideal gas equations, how to use them, and I have also discussed two numericals regarding that. There are certain conditions to use, but always remember you have to make a diagram and analyze the situation before proceeding to the solutions. Hope you like it. Thank you.